Hello, everyone. Thank you for joining us with our monthly Herbert-ABS HECSTAB webinar series. Today, we are going to be revisiting a subject that we gave a presentation on earlier this year, again, focusing on our Herbert-ABS wind software development. Back earlier this year, we did give a webinar on this. Since then, we have made a number of improvements and have actually officially released it into the public release as of last week or the week before. So for this one, we're going to be talking about less about the modeling of Herbert-ABS wind and more about just the application itself, the calculation methods and approach and visualization of results. With all that said, I'm going to turn this over to Brandon Wee, the primary Herbert-ABS HECSTAB product manager for HECSTAB and one of the main developers on this feature. So Brandon, I'll kick it off to you.
Thanks, Mike. Like you said, my name is Brandon Wee, and I'll be giving an introduction for our new wind analysis app, Herbert-ABS Wind. Going into a brief overview of what we're going to be talking about. Of course, we're going to be going over the Herbert-ABS Wind analysis tool. We'll talk about some of the modeling requirements and sort of considerations of building up your model before going into the wind app. We'll touch a bit on the methodology of our new wind analysis method, the 3D direct geometry. And then we'll actually run through a quick analysis and look at the various ways of visualizing results in the wind app. Afterwards, we'll move back into HECSTAB and we'll take a look at using 3D wind geometry in HECSTAB to do some analyses. So to give a brief look at some of our existing methods in terms of wind modeling and analysis, sort of three prior methods of doing this. First is, of course, the simple wind-defined method or user-defined method for just defining a wind moment. Next is the wind profile, which uses a profile in the transverse direction to do wind calculations. And this is typically used for just ship shapes and is limited to transverse winds. And the final one is the wind table, which is essentially a large matrix entry of wind overturning moments or force coefficients, depending on the analysis. And these tables can get quite large depending on how many different headings, drafts, trims, and heels you're looking at, as well as any different wind speeds. So our new approach for wind analysis is doing a direct geometry approach for the defined hull geometry, as well as any exposed cargo from loading conditions. And you can see on the visual on the right is our container ship demo with a loading condition attached to it to show different container stacks on deck. So moving into the modeling sort of considerations before moving into 3D wind geometry, this would all be done in Ship Project Editor under the Spaces panel in the hull. And so the first step is to define all your hull spaces in SPE. And so in the case of the model on the right here, we have our test semi-submersible model. And in terms of actual buoyant volumes, we have our deck, columns, and pontoon, as well as all of our topside geometry with the drill rig in the middle, a deck house, crane off the port side, and as well as a helipad. And so we'll give all our buoyant spaces the appropriate volume factor and any non-buoyant spaces on the top side with a 0 to show that they're just geometry for wind. After our geometry is defined, we'll go into apply our wind settings, which can be done by selecting the checkbox on top of the table to show the windage columns. And what that'll do is it'll expose the set of columns in the middle here for the various wind settings. The first one is our shape factor, which must be defined for any geometry that we want to consider for our wind calculation. And this is a multiplier typically given from regulations that apply to certain types of geometry. So there'll be shape factors defined for the columns, which will be different from the deck, and so on. Next is the wind permeability, which is another multiplier in the overturning moment calculation. And this is treated more as a design factor to consider how the actual part is built up. So say, for instance, on our crane, or on our crane arm, if this is a truss, open trussing, the wind is more able to pass through this rather than if it were a solid beam. And so the permeability can be applied to reduce the effects of the overturning moment because of how a piece is designed. Next column is the column to exclude individual components from shadowing, which accounts for how parts overlap when looking at the vessel in different orientations. And so we can do this here for just individual components. And finally, we have the idea of wind protected sides, which in the visual above is represented by the red X's on certain faces of these volumes. And the idea of wind protected sides is to not double count areas of two objects where they're butted up or joined to each other. So for the columns, we protect both the top, or we exclude both the top and bottom portions where they attach to the pontoons and the deck, so we don't double count those. And for instance, also on the drill rig and the deck house, we exclude the bottom face, so we're not double counting the area where the deck house meets the deck. And then once all of our hull spaces are defined, that's it for SPE. In terms of actually looking at cargo, those will come from loading conditions defined either in HECSTAB or HECSTAB. And we'll look into that when we move back into HECSTAB. Once our geometry is defined in terms of methodology, we move into generating the wind silhouette. And this is so that we can calculate both our areas, our projected areas, and our lever arms. So the first step here is to adjust the model to the desired draft, trim, and heel, or in the case of running HECSTAB, run the stability calculations for a given loading condition. Next, we use the wind heading to get the appropriate wind silhouette to look in the correct direction. And then from there, we project our area or project our volumes to get the silhouette that you see on the right here. And so here is our semi-submersible again from the previous slide, looking from port to starboard. For this step, it's important to note that there are some calculation settings available in both HECSTAB and the Wind app to set both the water plane calculation method and the trim axis type. And these two are important to look at as it changes how the vessel is rotated and adjusted into its end position based on draft, trim, and heel. Moving on with the wind calculation, we provide currently two methods on obtaining height coefficients for our different spaces. The first is the height coefficient lookup table, which is a predefined lookup table to determine a height coefficient for each component. And the second is the power law method, which divides the vessel into various strips from a user-defined strip height. And then for each strip, we take a reference height, reference speed, and a wind exponent, again, all defined by the user, and calculate a pseudo height coefficient for that strip. In the graphic on the right, you can see both methods overlaid on top of each other, the dashed curve and the sort of step function here representing the height coefficient. And this comes from the 2009 MODU code. And taking all those previous methods into account, we come up with our overturning moment calculation as shown above, where our K is a factor for air density and V is the wind velocity, which both come from the wind calculation settings. CS, which is our shape factor, and CP, our permeability, which come from the model settings. And then finally, the height coefficient CH, A, our projected area, and H, our vertical lever, which come from calculation. And we do this for each component of the hull and the cargo, if there is any, and sum those together to get our final result for the overturning moment for a given condition. So the 3D geometry wind approach builds up the basis for Herbert-ABS wind app, which is our user interface for calculating the effects of wind on a given vessel model. In the application, we can visualize wind effects for either individual cases or look at trends across multiple cases. And we can also generate wind tables for use in HECSTAB or HECSTAB, saving those directly to the model, and finally generate some summary result reports. In terms of visualizing results, we offer multiple ways to do so. The first one being both the 3D and 2D views of the model, which you can see on the top right. And here we have our wind direction shown with the blue arrow and our color shading on the 3D model representing the different shape factors. And then behind it, we have our 2D view, which shows what our actual projected area silhouette looks like. And this 2D view is also available separately, flattened out, instead of just being overlaid on the 3D view. Additionally, we have summary and detailed result tables. The summary table showing results for all the cases that are in the analysis, where the detailed result table shows the results for each specific component of a selected case. Next method is polar plots, which we can use to plot different result properties to look at trends across multiple cases. And you can see that on the bottom right, where we're looking at the wind arm on a selected draft and trim, and looking at our trends across our different heeling angles. And finally, we also support some Excel and Word export of the result tables for simple report printouts. That's about it for the presentation portion. Next, we'll dive into the wind analysis tool, and we'll look at the same semi-submersible model. We'll verify any of the space wind settings that are set on the model, go over the calculation settings available, and explain what they mean. We'll run a simple analysis and plot the results and view some reports to look at the visualization methods, and then we'll save out a model with the generated table and look at that model back in SPE. So I'll go ahead now and I'll open up the wind app, which I have here. And so you see our semi-submersible model here on the right. Our Herbert-ABS wind app, in terms of user interface, looks much like our new HECSTAB version 9, with the ribbon bar at the top to give a lot of the functionality, and then various panels for the different input and output from the program. Working our way counterclockwise from the top left panel, first we have our wind type settings, which give important settings for our wind calculation. Here we can give our wind type a name, define the speed that we're looking at, as well as the air density. For pressure distribution, which talks about how the pressure is distributed across the model vertically, we have two methods. One, the constant pressure distribution, the other being the gradient. You see if I select the constant pressure distribution, a lot of our initial calculation settings disappear since it's a much simpler calculation. Switching back to the gradient, we'll see the main one we come back with is our height coefficient, which has the two methods that we described previously, the wind exponent and reference height, or the power law, and also the predefined lookup table. With the wind exponent height coefficient method selected, you can see on the right, we have a convert button, which allows us to take the settings defined for the wind exponent and reference height and convert that back into a predefined lookup table, just to do some simple comparisons if needed. Moving on, we have our calculation methods for lateral resistance, which we offer 4 different types. First one, simple half drafts, which will place at half the draft of the current selected case. The projected area, which will actually use the projected underwater area in the model to calculate the CLR. The thruster center, which will use any thrusters defined in the model, which you can see with these orange circles. And it'll use where those thrusters are placed to act as additional resisting force to the wind force. And finally, the user-defined method to place the CLR at a given location below the water line. For data source, we offer, of course, the 3D geometry method, as well as the 2D wind profile to do some simple wind analyses for ship-shaped vessels. Next setting is the suppressed shadowing ability, which will do this globally across all of our models, all of our hull spaces in the model. With this setting applied, anything that was set in the model for individual spaces will be overwritten or will be ignored, and this one will take precedence. And then the next two are water plane calculation method and our trim axis type, which will determine how we obtain the vessel position. For the water plane calculation method, there are really 2 approaches here. The first is the wind system using the draft, heel, and trim. And the second is the wind system looking at a constant upright displacement method. So in the wind system, we first adjust the vessel down to a given draft. Then we apply heel based on the wind direction. So in this case, heel in the positive direction will be away from the wind, and heel in the negative direction will be towards the wind. And then trim is applied considering the right-hand rule from the wind direction. Next, for the trim axis type, we offer 2 approaches that again come from the same HECSTAB settings. One being the original trim axis and the other being the heel rotated trim axis. For this, it's easiest to think about this in terms of a vessel heeled over to 90 degrees. In the original trim axis method, with a vessel heeled over at 90 degrees, any trim applied will essentially be rotating the vessel around in the water and not really change any stability. Whereas the heel rotated trim axis will keep the trim axis perpendicular, so any trim applied with the vessel heeled over at 90 degrees will actually look like it's trimming and change its stability. And finally, in the wind type settings, for now we have the cargo panels shown here, which gives us any of the cargo that we've brought in from a wind project. Next, we have our wind parameters, which is essentially defining our wind table. Here we can select any of our different wind types if we have multiple different settings for a wind type. Next is our headings, heels, draft and trim selection. And here, if we make any sort of selection, you'll see that our 3D view will update to the corresponding selection. These parameters can be changed up here in the configuration for each section. I'll go ahead and for our wind headings, I'll do 15-degree steps from 0 to 345, so essentially all the way around the vessel. For drafts, I'll leave just the single draft. Heels, I will change this so we're only looking away from the wind. So I'll do every 5 degrees from 0 to 30. And I'll keep our trim settings the same. Moving on here, we have our spaces panel, which is a simpler version of the table that we saw in SPE. Here we have the name of the given space, our shape factor, permeability, the individual component shadowing settings, and then finally our wind protected sides. And these last 4 columns are editable from the Wind app, and the settings applied here can actually be saved out to a new ship model. And we allowed this just so that you don't have to go back and forth between Ship Project Editor and the Wind app in case you're just changing some simple settings for a couple compartments. Here for the wind protected sides, you can see those represented by the sort of magenta outlines of a given side. So from here, looking at our space settings, everything looks okay. We've set up our wind parameters as we wanted. And we'll leave the default settings here in our wind type settings for now. So we'll go ahead and click the run calc to run all of our cases. So you'll see we'll wait for this to finish up, going through each of these cases here. And we know that we finished running and our results are good with the green check mark shown all around. If I were to go ahead and change either some of our calc settings or add a couple new configurations, you'll see what we saw before with the yellow sort of diamond with the exclamation point, which is saying that any of the results that we see don't reflect the current calculation settings that are shown, and so we'd have to rerun to reflect the new settings. In terms of looking at results, we'll start with the 3D view. You can see this is now updated with our coloring. This coloring shows the different range of shape factors, green being the sort of lowest one and moving more red towards our higher shape factors. Here we have the 3D view and also the 2D view behind it. One of the settings available in the 3D view is to align to wind, which will point the camera in the direction of the wind. And this will change as we go around our different headings. We can have the show results behind it to show the 2D results, just so we can look and see if there's any overlaps missing, or if our 2D profile, say, had an extra rectangle here, we'd look at why that is to see any errors in our analysis. From here, the overlay looks good. We don't see anything coming out from behind with the 2D view. The 2D view is also available here, just on its own, to show the different polygons and the silhouette that we're considering for the hull. Back on the bottom panel, we have our detailed results, which looks at the selected condition. So we're looking at the 120-degree heading. There is some heel, I believe it's 10. That changed on me, but we'll look at 10 degrees heel. We have our single draft selected. and our minus 10 degrees trim selected. And so we can look at in the top row, it shows us again what condition we're looking at and gives some summary information on the displacement as well as the wind arm. In the main table below, we have first our projected areas for each different object. So we have our crane, which is now highlighted in yellow to show it's selected, and all our other components. You can see some of these have a drop down. So any component that's divided up based on the height coefficient method selected can be expanded down to show details for the individual polygons that make up that component. The next tab, that's distance, which for now just shows the projected area since that's the method we selected. It shows what the actual resisting force is of the underwater area, as well as the CLR. If we had selected thrusters to be used as the center of lateral resistance, they'll be shown as additional rows. And the max thrust that's available, if that's defined in the model, will be used to consider the available resisting force. Moving on to the additional visualization methods. First is our summary table, which is an additional pop-up under the View tab. And this will give a large table of all of our conditions and basically a summary of those important result values for each case. Additionally, we have the polar plot, which is another pop-up. And here we can select different properties we want to show in the plot. We have our wind arm, wind force, the overturning moment, center of lateral resistance, vertical center, and the projected areas both above and below. And so we can switch through these and get a sense of the trends that we want to look at, either in the different heading directions, in this case across different heels, or if we wanted to do so, we could also look at trends across different trims. Although as you can see, as we get more trims or more heels, this plot can get quite cluttered. So I usually like to keep this at the selected draft and trim and just look at trends across different heel. This plot can be saved out, I believe. Yep, so if we right click, we can actually copy this to the clipboard and get an image of this plot out into, say, Word for a report. Looking at reports, if I go into the File button above and to export, we have the two options here. The first, the CSV to go out to Excel, which will give us our summary results table, as well as a formatted report in the docx Word format. So if I go to export to Excel, either of these will come up with the save dialog. I'll save this as semi-table, hit OK to save. And if I go to open the semi-table, we'll see we'll open up Excel, and it'll give us the wind settings for the given table, and then our copy of the results table. So we can use this here to do any additional plotting in Excel. The Word report looks essentially like this, just formatted a little better and of course brought into Word. And so finally, with our analysis run, and if we think everything looks okay, we can go into File, Save As, and we can save a copy of this model out. And what this will do is it'll create a new copy of the model. Oops. A new copy of the model with the wind table. So I'll save this as semi-wind table. Hit OK to save it. Oops. I lost that window. Wind table. So what this is telling me is that any of the wind results that are in the current ship model are going to be overwritten with the new results that we have, and asking me if I want to continue with that. So that'll hit yes to save it. And like I said, what that will do is it'll overwrite the wind table with these new values and any of the settings here. So mainly the wind speed, as well as save any changes we made in the spaces tab. So if we change the shape factor for some reason, that'll also get saved out from the model. So we can go back to our folder and open up the new model with the wind table. Give Ship Project Editor a bit to load. Up on my other screen. So here we brought in our semi with the wind table saved out. Go to wind table, we can see we have all of the wind directions, heels, the draft, and trims, our wind speed defined. And if we go into our moment entry, we now have a filled out table with the results from the wind app. And so now this wind table can be used in HECSTAB or HECSTAB to do a wind analysis using just the table lookup if we wanted to do so. Of course, with the 3D geometry, we can also do that directly in HECSTAB. So now we'll move over to HECSTAB and look at our container ship model and try to do some wind analysis from here. So from here, I'll go ahead and bring in a few loading conditions that have cargo defined. I'll do just the two here. You'll see these will load in. We'll look at example 1, which is just the case with our container ship loaded down with some deck cargo, and I believe there's some in the holds as well. I want to clean up this view a little bit just so that we can focus on the ship and the cargo. Turn off our tool geometry, turn down our water plane, just so that this is a bit simpler. In terms of calculation settings, in the general settings, I'll reset the trim stability calculation to intact direct for both of these. Just so that we take settings from our start condition. And at the top level, I'll go ahead and define our wind. And here you'll see the sort of similar setup of the wind settings as from the wind app. Here we want to do our direct 3D wind geometry. We'll keep everything the same. And then additionally, we have this setting for exposed cargo handling. And we have two methods here. The first one, that's the default, is the upright lateral of the exposed cargo area and the arm. And this will work only for beam winds, and essentially taking the profile of any exposed cargo on deck. And so that would be appropriate for any ship-shaped vessels. But if we did have cargo defined on something more of an offshore type, or if we just want to do the 3D geometry approach for cargo, we can do so by selecting the direct 3D using cargo bounding boxes. And what this will do, if I select a condition with cargo and go into the loads tab, for any of our exposed cargo, so looking at the on deck loads, we have some columns here that show what is exposed, which any of these checkboxes represent. And this will essentially create new spaces for each of these cargo items based on the bounding box. So the fore and aft bounds, the port starboard bounds, and then using these two values here. First, the exposed stack lower, so the lower bound of the exposed stack, and then the height of the exposed stack. So this one vertically extend from this 26.1 above deck or above baseline to the 36.5 above baseline. And I believe for cargo, we do this exposure for container loads, some select bulk cargoes, as well as any defined miscellaneous weights. So the last thing I'll do here is, so under our start condition tools, we'll go ahead and add a writing arm criteria with wind applied. So go to browse, and under my writing arm criteria, use the IMO IS code 2.3, which will add this to our start condition and flow down to our two examples with cargo loading. From there, I'll go ahead and now run our two conditions. First one, our start being not our exciting condition, but we'll let the two examples run through and actually see what the 3D geometry brings in for us. So under examples, we have our IS23 weather criteria. And you can see now for our wind, we have this one line item for the wind heeling arm upright. If I expand that down, you can see we're using the 3D geometry and gives us an output of what the calc settings were for that 3D geometry calculation. And additionally, you can see here, we're using for our cargo, the cargo bounding boxes. And it gives us a summary of how many items were actually converted into spaces to use for the wind calculation. Gives us the projected area of just the cargo, and then calculate out the VCF, the overturning moment of just the cargo, and then the contributions from both the hull and the cargo into our overall overturn healing moment. One feature that we're currently working on is actually taking this loading condition and bringing it back into the wind app if we want to dive deeper into just this one condition. And so if I go back to our calculation settings under wind, we have this option here. This is currently in the release version to transfer our settings to the wind app. And what it'll do if I select that is it'll prompt me to save out a wind project, which is what we use for the wind app. I'll go into my save file and I'll save this out as LC1. Hit OK. What this will do is it'll take the wind settings applied here. It'll take my loading condition and create a wind project from that. And I'll open back up the Wind app. Instead, I'll File, Open, and I'll open up our new model, which is the container ship. Wait for it to come in. Close off these pop-up tabs. So we need to work on clearing our results out, but here I've come in with my container ship now. See here in the updated spaces tab, and go to back to File, and we'll open that Wind project that we saved up. So we don't want to save any changes there, and we'll open up our LC1 Wind project, and we'll see here a similar but slightly modified view than what we saw before with especially our Wind parameters. First off, you'll notice that our cargo column is now filled up with any of our cargo items that came in from that loading condition. But the biggest change is down here in our Wind parameters. So now instead of seeing the full matrix of heading, draft, trim, and heel, we have just a selection of cases with different heeling angles. And these heeling angles come from our stability settings in HECSTAB for our writing arm calculation. So here you see we have defined 0, 1, 5, 10, and so on. And that's what's brought into the Wind application here. Next, in our 3D view, you'll see that we have brought in now our cargo boxes as these new meshes from the given load condition. Here, if I go into run now these conditions here, you'll see that we come in now with both our hull and the cargo bounding boxes as part of our 3D wind calculation. And we can step through the different writing arms. I'll turn off this align to wind so we can stay in the sort of isometric view. And we can step through and look at either detailed results to compare it to what we had from our HECSTAB analysis, or just get a better sense of our wind effects as our vessel heels over. And so I think that's it for what I wanted to present today. I think so. Go ahead and take any questions if you have it, either on the Wind app or the interaction with HECSTAB.
Thanks, Brandon. There have been a couple of questions that have came in. I think in many cases they were questions that were came in prior to you showing the settings. So okay. Just looking at it, there was a question on the wind lever arm thruster point of action, and so I think you showed that we do have that option for accounting for the thrusters. Everyone that's here, while I'm going through these existing questions, please feel free to ask any others in the Q&A section on the Zoom toolbar itself. And there was a question on whether Herbert-ABS wind is only for offshore devices, and I think we've answered that as well. It's probably more applicable for offshore just because you're looking at things from many different angles and many different headings. But from a ship standpoint, obviously we just did some interesting things with the container ship as well. There was another question on the wind type settings to have an overall design factor, which I think you touched on as well. And then we've got one more that coming in here. The question is internal to the calculation, is the horizontal center of pressure calculated? I guess that's a question for you, Brandon.
The horizontal center of pressure, I don't believe it's calculated. We're looking more, especially in this 2D view, we're looking more vertically. If that's an output that we like to see in the calculations, I think we can talk further and then look at seeing what we need to change to either show that as output or and calculate that out.
All right. I think that's all the questions that we have now. Does anyone else have anything that they would like to bring up? We've got a few extra minutes here over our allotted time, but Brandon, is there anything else that you can think of that we can show with a little extra time, or should we just give it back to everyone?
At the moment, no, I think we've touched on everything I want to go through. Oh.
All right, so we have a question: which is the preferred input file type for the new model? So I'll let you explain that one, Brandon, a bit more, I guess.
Right. So in terms of the input model, it's the same ship project file, either the SH2 file, and really the main changes there are going into the hull spaces and applying the appropriate wind settings there, and then just saving out the same SH2 file.
And there's another question coming in. So if you were doing this all in HECSTAB with the direct calculation, how much of a time hit is it?
It's really dependent on the model complexity. We run into some models with very complex meshes, and trying to do a direct calculation there does take some time. It's doing a lot of silhouette calculations and trying to get any of these overlapping polygons. So if you're doing, say, like an intact, like max kg analysis for a vessel with very complex meshes, it may be preferred to go into the wind app, run the full table that you want to do, and save out the table directly to the model to run that in HECSTAB. Whereas if you're doing just a simple 1 or 2 loading conditions and trying to analyze the wind effects there, then the direct wind approach in HECSTAB would probably be preferred.
Okay, thanks, Brandon. I think that's, generally speaking, that's true for most of our calculations. The more complex the model, the more times calculations are going to take.